Hello all, welcome back. The next topic we have is homogeneous functions. A function f of xy of two variables, it is said to be a homogeneous function of degree n. For a homogeneous function, we define something called as a degree also. If f of xy can be expressed as x power n into some other function, I can take it as g also, f of y by x. That means I can take a x power n outside from this function f of xy, and the remaining function is going to look like a function of y by x. It is a function of single variable and that variable is y by x. The two variable function, I can write it as x power n into a function of single variable. The single variable is y by x. Then this x power n, the power of x what I have taken outside, it is said to be the degree of the homogeneous function. We shall see some examples also of this. Verify the following functions are homogeneous. F of xy is given to be x cube plus y cube by x minus y. So what shall I do is I want to put it in the form of y by x. So the complete x term on the numerator as well as in the denominator, I will take it outside. So x cube, if I take common in the numerator inside the bracket, then here x cube is taken outside, so 1 is going to remain. From y cube I have taken a x cube outside, that means I have multiplied and divided by x cube, and the division I have kept it as it is. The multiplication of x cube what I did, I have taken it outside. The same thing I have done with x minus y also. I've taken x common, x is taken common, so in the first term 1 is left. Here there is nothing left to take, there is no x at all. So if I have to take 1x outside, then I multiply and divide by 1x. The divided by x is as it is, and the multiplication by x whatever I have done, that x is taken outside. So this becomes x into 1 minus y by x. And here x cube by x, 1x gets cancelled, it becomes x square. And this numerator is 1 plus y cube by x cube can be written as y by x whole cube divided by 1 minus y by x. Now this is x square, and this complete function is a function of y by x only. There is only one variable, that is y by x. Therefore, x square into a function of y by x. Therefore, this is a homogeneous function of degree 2. Because the power of x what I've taken outside to make this function as a function of y by x is x power 2. So this is a homogeneous function of degree 2. Similarly, we will go into the second question. F of xy is cos x cube by plus y cube divided by x minus y. This is the same thing, x cube plus y cube divided by x minus y. Whatever I do, I can take x square into f of y by x, and but it is inside the cos only. I cannot take x square outside the cos. X square cannot be taken out here. It can be taken only in the argument. So I cannot write it as x square into a function of y by x. It is cos of x square into a function of y by x. It is not x square into cos of function of y by x. Therefore, this is not a homogeneous function. The third one is easy to observe, x square x power 4 minus y power 4 by x plus y. The same trick what we have done in the first problem. Complete of x I have to take outside. So if x power 4 I take outside completely, then I have 1 minus y power 4. There was no x power 4 to take outside here. So what I would have done, I would have multiplied and divided by x power 4. The division remains inside, what I've multiplied goes outside. The same thing with the denominator also, x power 4 and x, 1x gets cancelled, so that I have x cube into a function of y by x. Therefore, f of xy is a homogeneous function of what is the degree now? Because x cube is taken outside, the degree is equal to 3. Therefore, these are all examples of homogeneous functions. Then in homogeneous functions, we have an important theorem. That theorem is called as the Euler's theorem for homogeneous functions. What does the Euler's theorem state? It says that if u is equal to f of x y is a homogeneous function of degree n, then x dou u by dou x plus y dou u by dou y is equal to n into n. I can take the partial derivatives of u with respect to x and y. And for the partial derivative of x, I will multiply x. For the partial derivative of y, I will multiply y. And then add both of them. The value I get is the degree of the homogeneous function into the function itself. This is the Euler's theorem. Let's see the proof. The proof is also very simple. So what do I require in the proof? I should show that the left hand side is equal to right hand side. In the left hand side, I require two partial derivatives. Therefore, I will take the function u is equal to f of xy is a homogeneous function of degree n. And because it is homogeneous of degree n, u can be written as x power n into some function of y by x, some g of y by x. Then I will take the partial derivative with respect to x. Now this is a product of two functions, that is x power n and g of y by x. Therefore, keep the first function, differentiate the second function, g becomes g dash of y by x, and differentiation of y by x again with respect to x. Y is kept constant and differentiation of 1 by x becomes minus 1 by x square. Plus, the second function is kept constant. Differentiation of first function is x power n, that becomes n x power n minus. Rearrange, minus is taken in the first, y is taken in the first, x power n divided by x square becomes x power n minus 2 into g dash of y by x plus n into x power n minus 1 into g of y by x. Similarly, dou u by dou y. U is here. When I differentiate with respect to y, x is kept constant, or I can treat this as product rule only. Okay, I have taken this as product. So x power n is kept constant. G of y by x, differentiation with respect to y becomes g dash of y by x. Then differentiation of y by x with respect to y. 1 by x is kept constant, differentiation of y is 1. Plus, second function is kept constant. The first function is anyways a constant whose derivative is 0. Therefore, this becomes x power n divided by x becomes x power n minus 1 into g dash of y by x. Then, once I have both the partial derivatives, dou u by dou x, I should multiply by x. Dou u by dou y, I should multiply by y and then add both of them. So, that is what we have done in the next step. X dou u by dou x plus y dou u by dou y, x into this full term plus y into dou u by dou y is here. Now rearrange the terms. How many terms will I get? I have to multiply x to both the terms. X into x power n minus 2. One more x is there, therefore n minus 2 becomes n minus 1. Minus y is as it is, minus y into x power n minus 1 into g dash of y by x plus n into x and x power n minus 1 becomes x power n into g of y by x plus y into x power n minus 1 into g dash of y by x. Now these first and last terms are same, plus and minus, they get cancelled. So what is left is n into x power n into g of y by x. What is x power n into g of y by x? That is nothing but my function u. Therefore, x power n into g of y by x is nothing but my u. This proves the Euler's theorem. Euler's theorem is a very nice theorem. I can extend it to the second order partial derivatives also. So this is the extension of Euler's theorem. If u is equal to f of xy is a homogeneous function of degree n, then I can extend to the second order partial derivatives. There are three second order derivatives. One is the pure derivatives, dou square u by dou x square and dou square u by dou y square, and one is the mixed derivative. Therefore, x square, when it is x square in the partial derivative, then it is x square into dou square u by dou x square plus 2 times the mixed derivative, therefore 2 into xy into dou square u by dou x dou y plus the second partial derivative with respect to y. Therefore, this is y square into dou square u by dou y square is equal to n into n minus 1 into, this is the extension to higher order derivatives. Now we shall verify the Euler's theorem for a few functions. We shall start with the first problem. U is x power half plus y power half into x power n plus y power n. I should verify the Euler's theorem, that is nothing but x dou u by dou x plus y dou u by dou y should be equal to the degree of the homogeneous function into u. Therefore, I should first find what is the degree of the homogeneous function. First, I should check whether it is a homogeneous function. Then only I can apply the Euler's theorem. Therefore, first we shall check whether it is a homogeneous function. Take the function. So to check whether it is homogeneous, I should remove all powers of x in such a way that only y by x is left in the function. So I will take all powers of x outside from the first term. So x power half is taken outside. So it becomes 1 plus. The same trick, there is no x power half. Multiply and divide by x power half. Division is kept here, multiplication is taken outside. The same thing with the second one. X power n is taken outside, so I am left with 1 plus y power n by x power n. So x power half, x power n becomes x power n plus half into y by x. This becomes y by x power half. This becomes y by x power n. So this is completely a function of y by x. Therefore, this is x power n plus half into some function of y by x. So simply I write some g of y by x. It is some function of y by x. Therefore, this is a homogeneous function, and what is the degree? How much I have taken the power of x is n plus half. Therefore, the degree is n plus half. If the degree becomes n plus half, then the Euler's theorem says that x dou u by dou x plus y dou u by dou y is equal to n plus half into u. This is what we are supposed to verify. We should find dou u by dou x, dou u by dou y, then find the left hand side. I'll find dou u by dou x. So what we should do, this is a product of two functions. Keep the first part, differentiate the second one with respect to x. Y power n is constant. This is going to be 0. X power n is going to be n x power n minus 1. Let's keep the second term constant. Differentiation of the first one, y power half becomes 0. X power half becomes half x power minus half. This term is written front. This term is written front. Therefore, this is dou u by dou x. Similarly, find dou u by dou y. This is here. And x dou u by dou x plus y dou u by dou y. X into this is the dou u by dou x term plus y into this is the dou u by dou y term. Then we will multiply x here. X into x power n minus 1. 1 x is again added. So n minus 1 becomes n. So x into this becomes totally x power n. Similarly here x into this becomes how much? X into x power minus half. X power 1, x power minus half becomes x power plus half. So this is it here. N into x power n into x power half plus y power half plus half into x power half into x power minus half becomes x power plus half into x power 1 plus y power n. Multiply this, this becomes y power n plus n y power n. Multiply here, this becomes y power 1 minus half becomes plus half. Then check what is to be done. First two terms, anything common? No, here the terms are common. X power half plus y power half is common and n is also common. When I take n into x power half plus y power half common, here x power n is left plus here y power n is left. Similarly, here half is common. X power n plus y power n is common. Therefore, half into x power n plus y power n taken outside. Here x power half is left plus y power half. Then compare these two. What is common? These two terms are common. X power n plus y power n into x power half plus y power half is common. So if I take that common, here n is left plus here only half is left. This is nothing but u, therefore it is n plus half into u. That is nothing but our Euler's theorem. Second problem. U is x power 4 into log y by x. This is already given in the form of a y by x function. U is x power 4 into some function of y by x. Therefore, it is shown that it is a homogeneous function. And what is the degree? The degree of the homogeneous function is 4. Therefore, this is a homogeneous function of degree 4. Therefore, I should get in my Euler's theorem x dou u by dou x plus y dou u by dou y. I must get it as 4 into u. Then only Euler's theorem will be verified. So find dou u by dou x. Dou u by dou x becomes x power 4 is constant. Differentiation of log is 1 by x. variable is y by x. Therefore, 1 by y by x into differentiation of y by x. Y is constant. Differentiation of 1 by x is minus 1 by x square. Plus log y by x is constant. Differentiation of x power 4 is 4x cube. Simplify. This is going to be your dou u by dou x. Similarly, find dou u by dou y. When I find dou u by dou y, x power 4 is constant, log becomes 1 by y by x, and 1 by x is kept constant, differentiation of y is 1. Then you will simplify x power 4, y by x in the denominator becomes x by y into 1 by x. X gets cancelled, x power 4 by 5. Then find x dou u by dou x plus y dou u by dou y, x into this term plus y into the second term. Simplify. This becomes minus x power 4 plus 4 into x cube becomes x power 4 log y by x. Y gets cancelled plus x power 4. Minus x power 4 plus x power 4 becomes 0. So 4x power 4 log y by x. X power 4 log y by x is nothing but my u. Therefore 4 into u. Therefore the Euler's theorem is verified. You should be very careful while doing this because this is nothing but the degree of the homogeneous function, so that it changes for the function what you take whenever you verify. It is not a constant. So one more type of problem here. Function is given, you should show that this relation holds. This relation looks like the left hand side of Euler's theorem. So probably I can apply Euler's theorem over here. Okay. So that is the idea when we see this problem. Okay. This is how you make out whether it is a problem from the Euler's theorem. That means the left hand side will be of the form x dou u by dou x plus y dou u by dou y. Therefore it might be like the Euler's theorem. So let's start with the given function. U is sine inverse of x square plus y square by x plus y. So sine inverse, when I take it left side, it becomes sine u is equal to x square plus y square divided by x plus y. Now we have done this in the beginning once. When sine inverse of something is here, I cannot convert this into a homogeneous function directly, because whatever I do, I cannot take this x square outside, neither I can take this x outside. So this u is not a homogeneous function. So directly for u, I cannot apply the Euler's theorem. So I should convert it into some form so that I can apply the Euler's theorem. That is what we are doing in the first few steps. Sine inverse is there. I have taken it to the left side. So sine u is equal to x square plus y square divided by x plus y. And the sine u I have substituted as z. So when I put z as equal to sine u, left side becomes z. Z is equal to x square plus y square by x plus y. Now this, once I substitute for sine u as z, this will look like a nice function which we can convert it into a homogeneous function. I'll take x square outside, I'll take x outside, so the remaining is a function of y by x. So this is x square by x is x into a function of y by x. Therefore, now this z becomes a homogeneous function of degree 1, not u. So from u I have shifted to z. Z is a homogeneous function, so that I can apply my Euler's theorem to z and not for u. So by Euler's theorem for z, what is the degree? Degree is 1. So x dou z by dou x, for z it is now. X dou z by dou x plus y dou z by dou y is equal to, the degree is 1 into z. Using this relation, we shall prove the required relation now. So what is different now? Instead of dou u by dou x, I have got as dou z by dou x. That means I should work on this dou z by dou x. From where will I get dou z by dou x? From the relation for z is equal to sine u. Therefore, we will take z is equal to sine u. Find dou z by dou x. Sine u becomes cos u into differentiation of u becomes dou u by dou x. Similarly, dou z by dou y becomes dou by dou y of sine u, that is cos u dou u by dou y. Therefore, I will substitute for dou z by dou x and dou z by dou y here. X dou z by dou x is cos dou u by dou x plus y dou z by dou y is cos u dou u by dou y. And what is this left hand side from this relation? It is 1 into z, that is nothing but z. Therefore, z is equal to cos is common, therefore cos into Common I can take it. X dou u by dou x plus y into dou u by dou y. Therefore z is cos into this term. Substitute back for z. Z is sin u. Therefore x dou u by dou x plus y dou u by dou y. Cos taken this side becomes z by cos u. Z is sin u. Sin u by cos u is nothing but tan u. Therefore we get x dou u by dou x plus y dou u by dou y is equal to tan u, which is the required question. So what is the idea? We have taken the function. As such, the function is not a homogeneous function, and we have used the substitution method so that I get a new homogeneous function, apply Euler's theorem, and go back to my original function. The same thing here. U is equal to log of x power 4 plus y power 4 by x minus y. Looking at this and a question, x dou u by dou x plus y dou u by dou y. This is going to look like a Euler's theorem, but this is not a homogeneous function, because anything I do, I cannot take a power of x outside the log. Therefore, I have to rearrange this function. So what I have done, u is equal to log of something. This is nothing but changing to exponential form. E power u is equal to the argument. E power u is equal to x power 4 plus y power 4 by x minus 1. Now this log is removed off. Therefore, this I can make it as a homogeneous function provided I make a substitution for e power u. Therefore, take z is equal to e power u. Therefore, left side becomes z. Z is equal to x power 4 plus y power 4 by x minus y, which I can check whether it is a homogeneous function. It is a homogeneous function of degree 3. Therefore, z becomes a homogeneous function. We shall apply the Euler's theorem for z. Therefore, x dou z by dou x plus y dou z by dou y is equal to, what is the degree? Degree is 3. And we have applied for the function z. Therefore, right side becomes the degree into the function, that is 3z. Now, I wanted x dou u by dou x plus y dou u by dou y. I have x dou z by dou x and dou z by dou y. That means I should substitute for dou z by dou x and dou z by dou y. From where shall I substitute? From the relation z is equal to e power u. Write what is dou z by dou x? E power u into differentiation of u with respect to x. E power u into differentiation of u with respect to y. So substitute for dou z by dou x and dou z by dou y. Take e power u common. Substitute for z also as e power u. This is going to get cancelled. So x dou u by dou x plus y dou u by dou y is equal to 3. This is the required relation. This looks like Euler's theorem, but the function is not homogeneous, so that we should convert to homogeneous function and then obtain this relation. Similarly, I think the fourth one is proved. Fourth one, there is a slight hold over here. This is a function of y by x. This is a function of x by y. Therefore, this x by y, I will convert it into y by x. X by y becomes 1 by y by x. Once I do this, this entire thing is a function of y by x, so that immediately it becomes homogeneous. But there is no power of x taken outside. So what is the power of x taken outside? X power 0 into this entire thing is a function of y by x. So this u is directly a homogeneous function of degree 0. Therefore, by Euler's theorem, x dou u by dou x plus y dou u by dou y, what is the degree? Is 0 into the function u. So 0 into u is going to be 0. Therefore, this follows directly by Euler's theorem. Now this fifth problem, I will leave it to you. U is a function of 3 variables, and this looks like Euler's theorem for 3 variables. So you can either do it directly. This is the first part I have done directly. Take u. I want to u dou u by dou x, dou u by dou y, and dou u by dou z. So all the 3 derivatives I have done, and then x dou u by dou x plus y dou u by dou y plus z dou u by dou z into equal to, simplify, you will be getting the answer. Why I have done this is, this can be applied as Euler's theorem problem, or it can be done directly, because it is not asked that we use Euler's theorem anywhere. If you are getting confused, then you can do it directly, or if you use the Euler's theorem, it is going to look like this. You are applying the Euler's theorem for 3 variables x, y, and z. So take this u, take x cube common, so this will be y cube by x cube plus z cube by x cube minus 1 x. When I divide by x cube, 1 x is going to get cancelled. 2x are going to remain, that 2x are going to remain, and I'll write that 2x as y by x into z by x. Therefore, this u can be written as x cube into a function of y by x and z by x. This is the homogeneous function definition when I have three variables. uh, Three variables were there. When I removed x, it reduced to a function of two variables. That is the idea. When I have two variables f of x, y, when I remove x outside, it will reduce to a function of one variable. Then it becomes homogeneous. The same way, there were three variables. When I took x outside, x cube outside, it reduced to a function of two variables y by x and z by x. Therefore, it is homogeneous of degree 3. And by Euler's theorem, x dou u by dou x plus y dou u by dou y plus z dou u by dou z is equal to, the degree is 3, therefore 3 into. And the sixth one is can be taken as an extension of Euler's theorem or simply apply our Euler's theorem. If you look at the function, this is never going to be homogeneous. Therefore, what should I do? I can write it as tan u is equal to x cube plus y cube by x minus y. Then I should substitute for tan u as z. Then z is equal to this. Then z becomes homogeneous of degree 2 by the calculations what I have shown. Therefore, we shall apply Euler's theorem for z. So x dou z by dou x plus y dou z by dou y is equal to, the degree is 2 into the function is z. Then for dou z by dou x and dou z by dou y, we shall substitute. Z is equal to tan u. So differentiate dou z by dou x. Tan u becomes secant square u into dou u by dou x. Dou z by dou y becomes secant square u into dou u by dou y. Substitute dou z by dou x and dou z by dou y. Take secant square common. Then secant square, we take it divided here. Therefore, x dou u by dou x plus y dou u by dou y is equal to 2 tan u by secant square u. Secant 1 by secant square becomes cos square. Tan u becomes sin u by cos u. Cos cancels. So 2 sin u cos u. 2 sin u cos u is nothing but sin 2u. So if you take this, by Euler's theorem we had x dou u by dou x plus y dou u by dou y, 2 sin u cos u becomes sin 2u. Okay, take this relation and again partially differentiate with respect to x. This is again product rule. X is kept constant, dou u by dou x becomes dou square u by dou x square plus dou u by dou x into differentiation of x is 1 plus y dou u by dou y, again use product rule. Y into dou u by dou y differentiation with respect to x becomes dou square u by dou x dou y plus dou u by dou y into differentiation of y is 0. This side becomes sin 2u becomes 2 cos 2u into differentiation of u is dou u by dou x. In the next step, x dou square u by dou x square plus y into dou square u by dou x dou y. This dou u by dou x taken to the right side, taken common there. Dou u by dou x, when I took it common, 2 cos 2u, this became minus 1 over here. The same thing, take this relation, partially differentiate with respect to y. This is the relation you will get when you partially differentiate with respect to y. I have named them as 1 and 2. 1 multiplied by x, 2 multiplied by y. This is going to give me left side into x. So this is x into x square plus this becomes x into y becomes xy, x square and xy. Here the left side is multiplied by y. Therefore, this is going to be xy. This is going to be y square. Let's come to the right hand side now. This is going to be multiplied by x. Therefore, x into dou u by dou x into, this is nothing but 2 cos 2u. Make this as 2 cos 2u minus 1 plus y into this side. Y into dou u by dou y into 2 cos 2u minus 1. Now simplify xy, the same terms here. So 2xy dou square u by dou x dou y, x square dou square u by dou x square plus y square dou square u by dou y square. Okay, this is supposed to be 2. This is nothing but 2 over here. Therefore 2 cos 2u minus 1, 2 cos 2u minus 1. When I take it common, this is x dou u by dou x plus y dou u by dou y. This is nothing but sin 2u. Therefore 2 cos 2u minus 1. This cos 2u can be written as 1 minus 2 sin square u, sin 2u as it is. So when I multiply, 2 into 2 is 2, 2 into 1 is 2, minus 1 becomes 1. So this becomes minus 4 sine square u into sine 2u. Therefore, this is 1 minus 4 sine square u into sine 2u, which is nothing but the required question. So 1 minus 4 sine square into sine 2u. I think you'll have to just make this correction over here. This is 2 cos 2u, not 4 cos 2u. So this is, and you can directly apply the Euler's extension theorem, or if you don't want to apply the Euler's extension theorem, you will take the Euler's theorem as it is. Then what will you do? You will differentiate with respect to x, differentiate with respect to y, and then 1 into x plus 2 into y. This is going to give you the answer. That completes Euler's theorem for us. Thank you.